Hello people, welcome to Gurukula. I'm Jai. So today in this video we are going to cover the two-ray propagation model. So if you have not yet subscribed to the channel, please do consider subscribing, and now without any further delay let us get into the topic. So in our previous videos we might have formulated the path loss model for free space propagation. If you have not yet watched the free space propagation model, the link is already there on the top right corner, so you can always check out the video for free space propagation model. So the free space propagation model is found to be inaccurate because of certain assumptions that we made while formulating the path loss model. So free space propagation model assumes only the line of sight signal, and which is not found to be practical in most of the situations. So here in this two-ray ground reflection model or two-ray model, we are going to consider two rays or two waves that is going to reach our receiver from the transmitter. So one ray will be a direct line of sight signal, and the other ray will be a reflected signal, so that is reflected from the ground. So when compared between the two-ray propagation model and then the free space propagation model, the two-ray model found to be a little accurate since for the assumptions that we made. So now let us set up the environment for the two-ray propagation model. So this is the basic setup that we could do here. So it is as depicted in the figure. We could see that there is a transmitter on the left hand side, and then we could see that there is a receiver at the right hand side, and the transmitter is of the height ht and the receiver is of the height hr, and the transmitter and then the receiver is separated over a distance d. And you could see that there are two rays or two waves reaching from transmitter to receiver. The first ray will be a direct line of sight wave, which is represented, whose E field is given by ELOS, and then there is another wave that is reflected over the ground. The E field is represented. EI represents the E field for the incident wave, and ER represents the E field for the reflected wave. And for the sake of simplicity, we are going to consider ER is going to EG, where EG is the final reflected wave that reaches the receiver over here. And then furthermore, to get better understanding about the agenda, we will see HT represents the height of the transmitting antenna, HR represents the height of the receiving antenna, ELOS represents the E field of line of sight signal, and EG represents the E field of reflected signal, and where D represents the transmitter receiver separation or the distance between transmitter and then the reception. So as usual, we will make certain assumptions over here as we did for the free space propagation model, and the assumption goes like this. So first assumption that we make over here is the height of the antennas are larger than the wavelength of the propagating wave. That is, the height of the antennas, that means HT and HR, should be very larger than the wavelength lambda. So that is the very first assumption that we make. And the second assumption is the height of the antenna are lesser than the transmitter receiver separation. That is, the HT and HR should be very lesser than the distance between transmitting antenna and then the receiving antenna. Since this model we are going to formulate or we are going to use this model for finding out the path loss for most of the mobile communication systems, the distance between transmitting antenna and then the receiving antenna will be quite in terms of kilometers, approximately 10 to 15 kilometers. So the height of the transmitting antenna and receiving antenna should be very lesser than the distance between transmitting and then the receiving antenna. So that is the second assumption what we make. And the third assumptions, the reflected waves are considered as the grazing indices. So grazing indices occurs, this term is actually coming from the opticals, grazing indices, which means that actually the ray of incidence will be considered as grazing indices when the reflected wave is almost parallel to the ground plane. When the wave is almost parallel to the ground plane, we will call that as grazing indices. So when does this occurs? When the distance between transmitting antenna and then the receiving antenna is very high, then we could see that the reflected wave is almost parallel to the ground plane. So that is what the assumption made here. The reflected waves are always considered as an grazing indices. And also the fourth assumption is we are not considering the curvature of the earth. So since we are going to deal a maximum of 10 to 20 kilometers, in that 10 to 20 kilometers we could not observe the curvature of the earth. So that is the final assumption that we make. So to get further depth into the derivation part, we will formulate a flow for the derivation. So there are certain parameters for which we have to evaluate. The parameters to be evaluated are, we have to find out the E field for both the rays, for E line of sight signal and as well as the E reflected signal. So we have to find out the E field for both line of sight signal and as well as the reflected signal. That will be the first part. And the second parameter which we have to estimate is the path difference between the line of sight signal and as well as the reflected signal. And third one is the phase difference. As we always know that the signal, when it is getting reflected over a surface, then there will be a considerable change in the phase. So we have to consider the phase difference between the line of sight signal and as well as the reflected signal. And finally, the time delay. Since both the signals take different path, definitely there will be difference in time in reaching the receiver. So it is mandatory to consider the time delay as well, which is represented by tau d. So with this parameters to be estimated, let us get further into the derivation. So first of all, we will find out the E field for both line of sight signal and as well as the reflected signal. In order to find out the E field for the line of sight signal and then the reflected signal, it will be easy for us to start off with by representing the general equation for plane wave in free space. So the general equation in free space is given by E of, in terms of z and t, is equals to E naught times e to the power minus alpha z into cos of omega t minus beta z into ax, and ax is a vector quantity. So this equation we are very familiar with this particular equation, and this equation comes from the subject's electromagnetic fields or electromagnetic theory. So which is a general equation for a plane wave that is traveling on a free space. So now let us get into this particular equation and let us try to get what are all the various terms that is present over here. So E naught, that represents the amplitude of the wave, and the alpha represents the attenuation constant, and where the omega represents the frequency and beta represents the phase constant, whereas z represents the direction of propagation and ax represents the direction of E field variation. So with these parameters in mind, we very well know that this is a very basic equation for representing the ground wave. So now we will try to rewrite the above equation with our own variables. So the variables what we defined in the previous slide is just given here for reference, and when you try to rewrite the equation with our own variables, we will get E of d comma t is equals to E naught d naught divided by d times cos of omega c into t minus d over c. So this will be the equivalent equation for our E field wave. So you might be little unhappy with this particular term, whereas this seems not equal to this particular wave. So just for the sake of understanding, let me take only the cos term alone. So when you take only the cos term alone, I can multiply this omega c inside the braces, so that I will get omega ct minus omega c times d over c, and you could see that omega c can be replaced by 2 pi fc, and then this f by c can be replaced by lambda, where 2 pi by lambda is given by beta. So now I hope that you will be convinced that this particular equation is equivalent to this, so that I can conclude that these two equations is of the same form. And for the sake of simplicity, I am just eliminating the direction of the variation. So as of now, I am not considering any direction of variation since it is a vector quantity. Other than that, I am considering almost all the thing. E naught will be represented as E naught d naught divided by t, which represents the envelope of our signal, and cos term, this represents the phase part of our signal. So any signal should have the amplitude part and as well as the phase part. So that is what given over here in this particular equation. So now this d represents the distance between the transmitter and then the receiver. So now we can go ahead and then we can formulate what will be the E field for the line of sight signal and what will be the E field for the reflected signal. So what I will do is I will consider that the distance traveled by the line of sight signal, I will take it as d prime, and then the distance traveled by the reflected wave, I will consider that as d double prime. So when I replace d instead of d prime and then d double prime, I can find out the E field for the line of sight signal and as well as the reflected signal. So finding out the E field, For the line of sight signal, as I already mentioned, I have taken the distance traveled by the line of sight signal is d dash. So wherever I have d, I can replace that with d prime. So this will be my E field equation for my line of sight signal, and similarly I can replace d prime with d double prime, so that this represents the E field for reflected wave. And then you could observe that there is an additional term coming over here, capital gamma. So that is nothing but the reflection coefficient. So you can see that the reflected wave is getting reflected from the ground surfaces. So obviously it is mandatory for us to consider the reflection coefficient as well. So the ideal receiver, we all know that the ideal receiver will just sum up all the signals that we receive at the receiver end. So the end signal, which means the total E field of both line of sight signal and as well as the reflected signal, can be given as E total is equals to sum of E line of sight as well as EG. So in order to give the equation for E total, so I can substitute the values of E LOS and then EG over here. So we know the value for E LOS, which I can replace in terms of E LOS, plus you could see the value that is substituted for the EG as well. So this will be my final E total equation. And in order to take out the reflection coefficient by the loss of reflection from the dielectrics, we very well know that the value of reflection coefficient will be -1. So now by replacing -1 in this particular equation, I will be ending up with the final E total equation as this. So this is what the final E field which I will be receiving there at the receiver side. So E naught D naught divided by D prime cos of omega c times T minus D prime by C, minus E naught D naught divided by D prime cos of omega c T minus D prime divided by C. So the first term represents the E field for line of sight signal, and the second term represents the line of E field for the reflected signal. So now we will calculate the path difference between the transmitter the line of sight signal and as well as the reflected signal. So we already have this particular image. As you could see, the distance traveled by the line of sight signal is taken as d prime, and the distance traveled by the reflected wave is considered as d double prime. So calculating d prime will not be a bigger issue because it is of a straight line, so that I can easily calculate the distance traveled by this particular wave. But it will be quite little challenging when I try to compute what will be the distance traveled by this d double prime. So this complexity can be eliminated by incorporating a method called method of imaging. So this method of imaging is brought into the picture just to eliminate the complexity to find out this d double prime. So as per the method of imaging, what I will do is I will just take the mirror image of the setup what we have. So this is the setup what we already have. Now I will try to take the mirror image, which will something look like this. So the orange part represented in the figure represents the same picture that is on the black color. So this is just a mirror image what I have replicated over here. So doing so, you could see that this particular line, so this distance, only this particular distance can be equated to this particular line, so that what I can see is I could get a straight line like this, so that it will be easy for me to compute what will be the distance traveled by d double prime. So next, in order to find out the distance traveled by d prime and d double prime, I can use Pythagoras theorem to finding out d dash and then d double dash. So first of all, let us consider this particular triangle, particular right angle triangle. From this particular right angle triangle, I can happily formulate the value for d prime. So d prime is given by square root of ht minus hr whole squared plus d squared. So this particular side is ht minus hr, so root of ht minus hr the whole squared divided by this particular side, so that is nothing but the distance between transmitter and then the receiver, which is d. So this equation stands for d prime. Similarly, in the same fashion, in order to find out the distance traveled by the reflected path, I can consider this particular triangle now, so that from this particular triangle I can write d double prime is equals to root of ht plus hr the whole squared plus d squared. So already I have ht over here, and this particular part is equivalent to hr over here. So the total distance is ht plus hr. So ht plus hr the whole squared plus d squared will be my d double prime, and we always know that the path difference formula is, the formula to find out the path difference is del is equals to d double prime minus d prime. So in order to compute this, we will have to approximate, and then we will assume that the d is very larger than ht plus hr, which is already mentioned in the assumptions part. And by using the Taylor series approximation, we can find out what will be the total path difference. So this is what the final equation which I will get after substituting the values of d double prime and then d prime over here. So this is the value for d double prime and this is the value for d prime over here. So now what will I try to do is, I will try to approximate this equation, or I will try to simplify this particular equation. As a first step, I will take the d squared outside the roots. So taking the d squared outside the roots will result in this particular form of equation, and finally I will take out the roots as well. So by taking out the roots, my equation will take the form like this. So root is represented in terms of 1 by 2 here and as well as 1 by 2 here. So now by applying the well-known formulas here, a plus b the whole square and as well as a minus b the whole squared formula here, and you expand this equation and cancel out all the plus and minus hthr terms, the resulting terms will be 4 times hthr divided by 2d square. So this is what will be the final approximated equation what you will get after applying this a plus b whole squared formula and as well as a minus b whole squared formula over here. And then finally, by stepping ahead to cancel out this 4 and 2, the final path difference equation is approximated to 2 times of hthr divided by d. So this will be the final equation for path difference. So now let us march forward and then we will try to find out what will be the phase difference. So the phase difference is represented by using the term called theta del. So the theta del is given by 2 pi del divided by lambda, so which can be also represented like this, 2 pi lambda divided by c by f, where c by f is nothing but I have taken the value of lambda over here. So lambda is represented in terms of c by s as well, and then the final equation we can take it as 2 pi f del divided by c, and the final equation for theta del will be represented by omega c times del divided by c, where 2 pi f is represented as omega c. So that's the equation for phase difference. And finally, as a part of our flow of equation, we have to compute the last and final parameter, which is time delay. So the time delay is represented by tau d, and the tau d is can be represented like this, so del divided by c. So del divided by c, here I have represented the time delay in terms of path difference. I can also represent the time delay in terms of phase difference as well. So if I want to represent the time delay in terms of phase difference, you could see that it is theta del divided by 2 pi f. So time difference is not going to contribute much in our derivation, but still time delay plays a very important role when we are solving the problems related to a two-ray propagation model. So these are all the various terms which we wanted to compute to take it further, the two-ray propagation model. So just to summarize what we have seen, we have computed the value of E field total received at the receiver side. So E total can be given by E naught D naught divided by D prime cos of omega c times T minus D prime by C minus E naught D naught D prime cos of omega c times D minus D prime divided by C, whereas the first term represents the E field of line of sight signal and the second term represents the E field for the reflected signal. So this will be the total E field which I am going to receive at the receiver side. So finding out of E total is completed, and then we found out the path difference model. And then we found out the path difference which is approximated to a value 2 times hthr divided by d. So that is the path difference what we get after applying all the Taylor series approximation. And then we found out the phase difference. So phase difference theta del is given by omega c times del divided by c, where c is the velocity of wavelength, that is a constant, we all know that. And finally the time difference tau d. So tau d is equals to theta del divided by 2 pi f. So these are all the various parameters which we have to evaluate, and that has been found out here in this particular video. And in the next video we will try to make certain assumption, and we will try to incorporate all these values into this E total, and then we will formulate the path loss model. So here in this video, I'm going to end this video here, and the remaining part, formulating the path loss for two-ray propagation model, will be posted as a second part of the video. The second part of the video link is also given on the top right corner. You can always check it on the I button, so that it will be easy for you to continue with the derivation. So I will stop here. We will see in the next video. Until then, happy learning.